Hi everybody. Today I'm going to be talking about a system that allows us to find the cause of packet drops in networks. And as people who work on network diagnosis, our ultimate goal is to be able to find the cause of every packet drops that happens in our network. And this is an obviously hard problem to solve, right? Just look at the number of papers that are published every year in SIGCOMM and NSDI trying to solve this problem. And what I'll talk about today is how to find the cause of every TCP packet drops in particular in data center networks. And the reason we care about this problem is that we think not all failures are the same. And what do I mean by this? So take this particular case where we have a link that's dropping a lot of packets. And we might know about the existence of this link and that it's dropping packets, but customers whose connections are going over that link aren't really experiencing any problems, maybe because their applications aren't necessarily sensitive to network packet loss. On the other hand, we might have a particular customer who's complaining about his connections to service X having performance problems, and his problems are mainly due to another link that is dropping packet at a much lower rate, and that link might not be high up on our radar. And because fixing these links often takes time, because we also need to figure out why the link is dropping packets, then we want to be able to associate the failed links with the problem they're causing to be able to prioritize the links that we want to fix. So in an ideal scenario, we want to know that this failed link is impacting this particular customer, this other failed link is impacting this other customer, and prioritize our fixes accordingly. So how would I ideally do this? Let's assume for a second that we know about all of these failures. And let's assume I know that this guy has these connections, and I know which path those connections went over. So I know which link impacted this guy's connections, and similarly, I know which link impacted this other guy's connections. But the thing is, operators don't always know which links have failed either, right? So the reason this problem is hard is because data centers now operate at massive scales. We have millions of links, and a couple of them could be bad at any given point in time. And finding which links are bad is actually like finding a needle in a haystack. And what complicates the matter even worse is that data centers often operate on shallow buffers, which means that you can have one-off packet drops because of a buffer overflow, and those aren't really uncommon. And they act as noise for diagnosis, which means that we might often find those as being problematic, whereas there's nothing there for us to fix. The problem goes away on its own. So in this paper, when we talk about failures, what we really mean is a systemic cause of packet drops, that whether that's transient or not, but it's something that we can actually go and fix. So let me just repeat that for a second. So when we talk about failures, we're talking about systemic causes of packet drops. And when I talk about noise, what I mean is one-off packet drops because of the buffer overflowed. But it might not happen anytime soon again for the second time. So what I'm going to do in this talk is I'm first going to discuss what our requirements for a solution to this problem are. I'll then present a strawman solution to this problem. And then I'll talk about what our system does and how it finds the cause of every TCP packet drop, and then I'll go through the evaluation. So we have a set of requirements for a system that is able to do this, and our requirements are that, first of all, it should detect short-lived failures, it should detect concurrent failures, and it should be robust to noise. In addition to that, in an ideal scenario, we want to also avoid making any infrastructure changes because they're costly to implement and maintain, and sometimes they're not even an option. For example, if your destinations are outside of the data center, you're out of luck. So what we've managed to achieve is a system that doesn't require any changes to the destinations or to the network, but is something that we deploy across all hosts in Azure. So a strawman solution to this problem would be the following. Let me make some assumptions first. Let's assume we knew the path of all flows. I know this is a big assumption, but let's assume that's true for the time being. And let's assume we know of every single packet drop that happens in the data center. Well, tomography approaches would then be able to find the cause of failures if we assume we have enough flows. So here's how that will work in practice. Let's take this toy example, and let's assume the link between 4 and 2 is failed. If I have 1 connection between node 1 and 3, that connection is not seeing any packet drops. The second connection goes from node 1 to 2, it has some packet drops. Third connection goes from 3 to 2, again has some packet drops. I can assign a variable to each of my links, And each variable xij is 0 if the link is not dropping any packets, and is 1 if the link is dropping packets. And what we want to find is what is the right value for xij for each of the links in my network. What I can do is I can write an equation for each of my connections where basically the OR of all the variables for all the links that each connection goes through is equal to whether the connection experienced a packet drop or not. And if I can solve this system of equation, where in this case I can't because I'm one equation short, I would be able to figure out which links are dropping packets. So to be able to do that, I need n solvable equations, n independent equations, where n is the number of links in my network. So as I sort of alluded to in the previous slide, there are theoretical and practical challenges associated with being able to do this in practice. So the theoretical challenges is what we saw in the previous slide. You need to have enough equations to be able to figure out what link has failed. And the way tomography gets around this is that we add an assumption. The assumption is the minimum number of links that explain all failures are the actual failed links. So one approximate solution to that is a max coverage algorithm, which past approaches have used for their diagnosis algorithms. The problem with those approximations is that they're sensitive to the noisy drops that I mentioned earlier, and I'll show you more about this in the evaluations. And in addition to all of these problems, the approaches are based on two assumptions. One, they assume a small number of failed links. Second, they assume fate sharing across all flows. And we'll talk about this more throughout this talk. There's also other practical challenges, which are engineering challenges associated with doing tomography. So I mentioned one assumption, which was we know the path of all flows. So how can I actually get the path of all flows? One way of doing it is to pre-compute all path by, let's say, asking my vendors to give me what their ECMP functions are. The problem with doing that is ECMP changes with every reboot of the switch. And link failures just complicate the matter because the set of links available to your function changes. And it's hard to keep track of these in real time. I can do something like a traceroute. The problem is that when I send a traceroute message, the switch has to respond with an ICMP message, which goes through the switch CPU and can overload the switch CPU. So the other problem with a traceroute is that you need to deal with NATs and software load balancers. Finally, I can do things like label packets, add metadata, but that requires infrastructure changes, which we wanted to avoid. So what I'll show in this talk is our system. We call it 007. And what it does is that it's a simple traceroute-based solution. It has minimal overhead on the switches. It's tractable. It's not NP hard. It's resilient to noise. And it requires no infrastructure changes beyond a host-based application. And we proved that it's actually correct. So you might have noticed that 2 seconds ago, I said that traceroute is not practical to find the path of all flows. Then how is it that I'm actually using traceroute for 007? Well, so we had to deal with two challenges, right? First one was we have to deal with the fact that traceroutes overload the switch CPU. So what we've compromised on is that we don't track the path of all flows. We only track the path of a flow if it had at least one retransmission. And we limit the number of traceroutes we allow each host to generate. And even before 007 came along, there were ACLs on the switches that prevented the switch from responding to too many traceroute messages. We also need to deal with NATs and software load balancers. So in essence, what we do is we send traceroute messages whose headers match exactly that of the flow's packet headers. But for details about how we do this, I'll refer you to the paper because that's a long story in and of itself. So how the system works in practice is as follows. We have a host-based application that's deployed across all hosts in Azure. And when you have a connection, it gets a notification every time that connection experiences a retransmission through a publish-subscribe messaging system in Windows called ETW. And once we get notification of a retransmission, we send a traceroute message to get the path of those flows. And then connections simply vote on whether or not the links along their path were good or bad. And while you don't know which link on your path is dropping packets, so what a vote means is that if you don't know who to blame, just blame everyone for now. So here's how the voting scheme actually works. So here we had one connection between node 1 and 3. I assign a vote of 0 to all of the links involved. Now I don't know the actual path because I'm not doing trace routes for connections that didn't have a packet drop. But 0 plus 0 is 0, right? So I don't actually need to. The votes here are implicit. But for connections that did have a packet drop, I get the connections to vote. And even though I couldn't find the failed link before with those equations that I showed earlier, here I know that the link 4.2 is the one that's actually dropping packets. So democracy works. So can we diagnose TCP flows now using this method? So we have votes, right? So if we assume that there's fate sharing, we can compare the drop rates of each of the links that are involved in each connection. So for each flow that had packet drops, we actually know the path now, right? So the link with the most votes is the most likely culprit here. And we've removed one assumption. So we still have to make that fate sharing assumption that tomography makes. So this approach doesn't eliminate that, but we've eliminated the assumption that the smallest number of failed links are the ones that have actually failed. So some attractive features of this approach is that it's resilient to noise. It's very intuitive. We all understand how it works, and it's easy to implement, and it requires no changes to the network. We also give theoretical guarantees, so it's not like you should trust me that this works. You can go and read the proof for why it does. We ensure, first of all, that there's minimal impacts on the switch CPU based on some theoretical bounds, but we also prove that the voting scheme is 100% accurate, depending on a certain bound. So if we have noisy links, the only requirement is the failed links that you want to find have a drop rate that is different from those noisy probability of noise with a certain degree. And that bound depends on the topology of your network. So let's evaluate this and see if it actually works in practice. So first of all, the first question is, if I'm doing traceroute to find the path, am I reactive enough to be able to find the actual correct path? Does the failure change my path, right? Can I find the cause of packet drops for each flow correctly? Are votes a good indicator of packet drop rate? What level of noise can we tolerate? And what level of skew can we tolerate? And I'll talk about skew towards the end of the talk. So we first ran a 5-hour experiment. And what we did is we used a system called Everflow, which allows us to do packet captures on each switch in the network. And as you can imagine, it's costly, so I couldn't run this for a long period of time. And we compared the performance of 007 with that which we observed with Everflow. And the question we wanted to answer is, do traceroutes go over the right path? And does 007 find the cause of packet drops correctly? And we found the answer to both of these questions to be yes. We also had a 2-month deployment of 007 in one data center. And some of the problems that we managed to find were things like software bugs, FCS errors, which are fiber optic problems. We had route flaps and switch reconfigurations. The next question is, are votes correlated with packet drops? So in a test cluster, we induced packet drops on the Tor to T1 link, and we varied the drop rate from 1% down to 0.05%. And the last drop rate is where the bounds of the theorem I mentioned earlier now don't hold. And as you can see, for the first 2 cases, 007 is 100% accurate. But once I start to violate the constraints of that theorem, I start to see about 10% false positives. So for those of you who are interested in more details about this, what I've shown here is the distribution of the difference between the votes of the failed link and that of any of the other good links, the maximum of any of the other good links, which we don't want to detect. And as you can see, for first of all of the CDFs are moving towards the left, which is good, which means the votes are actually correlated with how bad the link is. But also, once we go we violate that bound, we have 10% false positives because the difference becomes negative. Finally, what I want to do is compare against that max coverage algorithm that I mentioned earlier. So max coverage, what we showed is that it's actually an approximate solution to a linear optimization program, which we call it the binary optimization. So you can look at the extended version of the paper for the proof of that. And we found that it was highly sensitive to noise. And I'll show results that show this in the next slide. But we took it upon ourselves to even improve upon that algorithm to see if we can actually fix it. So we took into account noise, and we tried to fix that. And while it did reduce the sensitivity somewhat, we still didn't manage to completely eliminate the variance we saw with these approaches. And I'll show you this also in a couple of slides. So we have a simulation setup, which is a class topology with 2 pods and over 4,000 links. We introduced drop rates between 10 to the minus 2% and 1% uniformly at random on all of the on some links. And we have noise that is uniformly at random distributed between 0 and 10 to the minus 4%. So here's just precision numbers for max coverage and the binary optimization. The recall for all of them are the same. So basically the way you should think about it is the cost of using this binary optimization is you get a lot of false positives. And the difference is about 75.3%. On the other hand, both the integer optimization problem and the 007 approach, both of them are working rather well. I also mentioned that we try to make sure that we're less sensitive to noise. And while that's true with the integer optimization problem, it's not completely eliminating that sensitivity in the sense that the integer optimization problem, while accurate, is highly sensitive to that and it has a high variance. But if you've been paying attention, one flaw exists in 007, and that is, what if I have skewed traffic? So let me show you how that will work, right? So I have a connection between 1 and 3. I have a connection again between 1 and 3. And finally, one between 3 and 1. None of my connections went through the failed link. So if I vote, I'm never going to find what the failed link was. And that's true. It is a flaw. In this particular case, I would argue that it doesn't matter because the failure isn't impacting any traffic. But it could have, right? So I need to show what would happen in practice. So in the same simulation scenario, what we tried to do was start to increase the level of skew by directing more and more traffic to a single TOR and check whether 007 can still perform accurately. So we went from 10% to 30% to 50% and then 70% skew. And as you can see, up to 50% skew, 007 is actually doing fine. For 50% skew and higher, and for higher number of failed links, we start to see problems. And as you can see, for example, for more than 10 links and for 70% skew, we're actually down to 50% accuracy. So in conclusion, what I've shown here is a simple voting-based scheme can actually work really well. It finds the cause of problems for each flow correctly. It allows operators to prioritize fixes, is analytically proven to be accurate, and is contained at the end host as an application, and it requires no changes to the network or to the destination. And with that, thank you.
We have time for quite a few questions, and I don't have chocolates. But yes, Ajay.
Hey, Ajay Mahim from AT&T. Today's data center networks and large carriers do have SNMP monitoring and syslogging. And so I'm trying to understand if the goal of the work was to try to discover these failures in the network using end host measurements, or was it to...
So it was both. So one, the main motivation was when you have problem for a specific application and you want to know what links are impacting that application to find what those links are and how much that link is impacting that application. But in addition to that, it also allows you to find failed links. And the reason this is important is that you might have, like, you can search for, like, I see an impact. I search my SNMP logs and I get 2,000, 20,000 SNMP messages back. How do I know which one to look at? So it helps with focusing your attention towards which parts of the network you should
But if I have to discover failed links, I can look in syslog and just look for link up-down message, right? And that will tell me what links have failed.
So it depends on what your definition. If you're looking for a link down event, that's true. But what we're looking at, and if you looked at the simulations, I'm looking at 10 to the minus 2% packet drop. So it's not failure in the sense of the link is down. It's failure in the sense that the link is dropping packets.
So even SNMP has packet errors and drop rates, right? So if you want to discover packet drops per link, you could use SNMP to calculate.
Yes, but then how do you know if that link is the one that you're actually looking for? In the sense that is that link the one that's impacting the particular application that is suffering right now?
Okay, because if the goal of the operator was to discover all the poor links in terms of either packet drops or link downs, and then prioritize, if your application was prioritizing the link failure resolution based on application impact, then yes, then that's good because you're starting from the link failure and looking at what applications are impacted.
Yeah, I mean, we've had war stories, and I don't know if I can talk about them, so you can talk about it to the Azure guys, and they can explain it much better than I can anyway. So I'll let them explain why this was necessary.
Okay, all right, thank you.
Hi, great talk. I was wondering if you are scheduling your trace routes in any way. Are you actually doing all-to-all measurement?
So it's not all-to-all measurement. So every time we get a retransmission notification, that's the only time we do a trace route. So it's immediately after a retransmission event, and once only for each connection.
I see. So it's only it's only when you suspect that there's a problem that
Yes,
you actually schedule.
yes, yes.
Hi, Peter Lopukov, Facebook. So my first question, that was great work. We really value all this kind of work that finds faults in the network. So how do you tell congestion from a link fault?
So essentially, and this is some of the prior work has shown this, like Mania Qobadi has a paper from SICOM this year, which is that we think that congestion drops are mostly low probability drops that kind of constitute as noise, so it's not going to even register with the system. The more severe cases of congestion, which are persistent, that have high probability, those we actually want to detect. So we're not saying we don't want to detect any congestion event. We only want to detect those congestion events that are actually causing severe problems.
So on the host side, can you tell, let's say, fast transmit versus RTO transmit? Which ones do you actually use? Because the RTO ones are much more like signal efficient, right?
So we're using the ECW in Windows, which I believe is fast retransmit. I have to go and double check to make sure that that's true.
Yeah, this is my main question, because we had similar systems, and the major problem is handling the congestion versus a link fault. The fault, because packet drops may be caused by either, and the other problem is if you have a heavy congestion, you get lots of retransmits, right? So how do you rate limit those? How do you control
So we do have a bound. So we bound the number of retransmits we're allowed. So the number of trace routes we are allowed to generate from each host. And what we've basically done is showed that the number that we are allowing on each host is enough to be able to make an accurate diagnosis. In addition to that, we're only limiting the number of trace routes we do for each flow to only one.
I see.
So we don't do more than one trace route for a single flow in a certain epoch, not forever, but like.
Thank you.
Yes. Okay, thanks.
Okay. Thank you, Behnaz. Our next speaker is Ife Yuan. I'm wondering if I should talk about this session as a faculty candidate, coming up faculty